Hello students, welcome back. In this session, we will solve some more important questions from the alcohols, phenols and ethers chapter to help you prepare for your exams. I strongly believe that the more questions you practice, the better you perform in the exam. So, let's sharpen our concepts and boost our confidence together. Are you ready to learn and score better? Let's get started. The first question is based on the alcohols and stability of the hydrate. First, what is a hydrate molecule? In organic chemistry, whenever there is a carbonyl compound like aldehyde or ketone, and when water is added to it, it's going to form an addition product, and we call this as a hydrate. You can see this water will add to the double bond here, the carbonyl carbon, right? And it's going to form a geminal diol, and this geminal diol is called as hydrate. Now, since the question is about the stability of the hydrate, we have to see whether this hydrate is stable or not. Most of the time, the hydrates are not stable because the carbon having two hydroxyl group is highly electron deficient because oxygen is electronegative. It withdraws electron from the carbon. So because of this, there is a possibility of it undergoing dehydration and it will revert to the corresponding carbonyl component water. And what do you call this as? We call this as equilibrium. So the hydrate formation is generally reversible. That's why we call this as equilibrium. Then how do you explain the stability of the given molecules? For this, you need to know some of the exception cases. For example, the first molecule is a geminal diol of a cyclopropane. Is this stable now? In order to understand this, let's form the carbonyl compound after dehydration. So what I meant is, say when this undergo dehydration, what we are going to get? We are going to get the cyclopropanone. Now, among these two, which is more stable? How do we decide? Let's understand the structure in detail. For example, the carbonyl carbon, we know that here it is sp2 hybridized. And whenever it is sp2 hybridized, what is the bond angle expectation? 120 degree. But generally, in a triangle, what will be the bond angle here? It will be 60 degree. What is the deviation now? 120 to 60 degree. There is a huge bond angle deviation which causes ring strain in the molecule. If there is a ring strain, do you think this molecule is stable? No, this cannot be stable. It will revert to the hydrate molecule. In hydrate molecule, the carbon here is sp3 hybridized. Whenever the carbon is sp3 hybridized, the expected bond angle is 109.5 degree. Right? So compare the bond angles now. Which is closer to 120? Obviously 109.5 degrees. So less ring strain in the molecule. Hence, it prefers to be sp3 hybridized. That means it prefers to be a hydrate rather than a ketone molecule. Hence, this is stable as compared to its corresponding carbonyl compound. But whenever you see all of these options, it's always better to check for the other two molecules also. So let's check for the hydrate of a chloral molecule. What do you mean by that? See, when carbon is attached to three chlorines like this and there is an aldehyde like this, we call this as a chloral molecule. Al refers to there is an aldehyde in the molecule, and when we add water to this, what we are going to get? We are going to get a hydrate molecule. Now, is this stable in some way? Yes, it is stable because of the intramolecular hydrogen bonding. Generally, chlorine doesn't exhibit hydrogen bonding. What elements exhibit hydrogen bonding? Fluorine, oxygen, and nitrogen. But the electronegativity of nitrogen is almost equal to that of the chlorine. Because of this, in this case, it does exhibit intramolecular hydrogen bonding. How so? Oxygen is an electronegative element and it makes hydrogen electropositive, and chlorine is already electronegative and it start interacting over here and it forms a cyclic structure like this. And due to this cyclic structure, it's imparting extra stability to the molecule. Hence, chloral is also stable. If A and B both are stable as hydrate, Obviously, the ninhydrin molecule, this is called as ninhydrin, is also stable. But what is the reason? You can see that this also exhibit intramolecular hydrogen bonding like this. Hence, what should be the correct answer here? All of these. The next question is purely based on the reaction mechanism. You can see that there is an epoxide with halogen in it and it is treated with sodium methoxide, and we have to find out what is the major product. Before we start writing the mechanism, first let's understand what is this oxygen 18 carbon 14. So these are nothing but isotopes of oxygen 16 and carbon 12. Then why are we using these isotopes here specifically? To know the mechanism of the reaction. So in order to understand what sort of reaction path the molecule is taking place and to differentiate the atoms, we use the radioactive elements like oxygen 89, carbon 14. So here this carbon 14 differentiate from the other two carbons, and this oxygen 18 differs from the oxygen from the methoxide. So what sort of reaction will take place now? Let's start predicting. Methoxide is a nucleophile, and where the nucleophile will attack, it will always attack the electrophilic carbon. Where do we have electrophilic carbon in the molecule? You see, oxygen is electronegative element and both the carbons from the epoxide are electrophilic in nature. And what about the chlorine? Chlorine is also electronegative, making this carbon electrophilic. Now you see all the three carbons are electrophilic. So we don't know where this methoxide will attack. So that is the reason we are using the labeled atoms. Labeled atoms refers to isotopic radioactive elements here. Now let's rule out this carbon. Why so? Because oxygen is more electronegative than chlorine. So it makes these two carbon more electrophilic. Therefore, we can rule out this option. Let's see where this methoxide will attack between these two electrophilic carbons. It will attack where there is a less steric hindrance. And where is less steric hindrance? On this carbon. Therefore, this bond will open up. And how to write the product? Based on the arrows we have used. You see, this is the carbon where the methoxide attacked. So here we are getting ether. What about here? We are getting O minus, and this is labeled oxygen, right? Therefore, let's write it as O18. And what about here? This carbon is attached to one more labeled carbon, that is carbon 14, which in turn attached to the chlorine here like this. How many carbons do we have here? 1, 2, 3, except for the methoxide. And since negatively charged species is attacking on a neutral molecule, we should end up with the negatively charged molecule. And what should happen? You look at the options, right? So again, we are getting ether, right, in three options. So let's try to generate ether. Why again ether will be formed? Because when the negative charge on this labeled oxygen attacks here, chlorine is a good leaving group. It will leave the molecule. And what sort of product are we going to get? Ether again, right? Like this. And this in turn, you can see it is attached to a carbon here and ether here like this. All put together in the longest chain, still we have 3 carbon. And where is the labeled oxygen? Here. And where is the labeled carbon? Here, like this. So oxygen 18, carbon 14 must be adjacent to each other. And where do we have it? In option A. Therefore, this is the correct answer. Let's find out what is the major product for the given sequence of reactions. The reactant molecule is a paranitrophenol. When it is treated with the sodium hydroxide, it is acidic enough to react with the sodium hydroxide and it will form para-nitrophenoxide ion. So it will be a sodium phenoxide ion which will act as a nucleophile generally, and it will attack the ethyl bromide or bromoethane because the carbon present here is electrophilic. Therefore, this will undergo nucleophilic substitution reaction. So what you are going to get? You are going to get ether. So this is one of the methods to prepare aromatic ether. When this is treated with lithium aluminum hydride, where is the reactive center? Ethers are not reactive with lithium aluminum hydride because this is also electron rich, this is also electron rich, but rather it will reduce the nitro group to amine. So you can see that we are going to get aniline like this. This is a para-ethoxy aniline molecule. And finally, what is the last reaction? We are treating it with acetic anhydride in pyridine. So pyridine is a basic medium here and it will do the acetylation on the nitrogen. So you can see here we are going to get N-acetyl product. And where do we have it? Let's check in the options. So you can see this is tri-substituted. So you can ignore this. And look at this OC2H5 means what? It's the ethyl ether. And what about here? We have the acetylation product. Therefore, the final answer is option B. The next question is based on the reaction of the given unsymmetrical ether with the hydroiodic acid. This is one of the most frequently asked concepts in the exam. How to cleave this molecule? You can cleave it either here or here. But whenever you have aryl alkyl ether, it's always recommended to break the bond over here, but not here. Why is it so? Because of the resonance effect. The lone pair of electrons present on oxygen is exhibiting resonance, that is plus R effect. Because of this, there is a partial double bond, and we know that it's difficult to break a double bond rather than a single bond. Once this ether gets protonated over here, the bond will break and the iodide will attack over here through SN2 mechanism. Therefore, you are going to get a phenol. Remember, whenever there is a aryl alkyl ether, one of the products will be always a phenol as the bond breaks here. And what will be the other product? You can see that the benzene ring will remain as it is. There is nothing change with respect to nitro. And what about here? CH2, CH2, iodine like this. And check for the options now. Here benzyl alcohol is there, not possible. Phenyl iodide, not possible. What about here? You see NO2PH, CH2, CH2, iodine. So where do we have it? In option D, but not C. Therefore, the correct option is D. The last question is based on the acidic strength of phenols. You have to arrange the given molecules in the decreasing order of their acidic strength. First of all, why phenols are acidic? Because they can donate the proton and form a stable conjugate base. Why is this stable? Because it can undergo resonance on the benzene ring and stabilize the negative charge. And remember, they're not acidic enough to react with sodium bicarbonate. They're acidic enough to react with sodium hydroxide, sodium, etc. Now, what will affect their acidic strength? It mainly depends on the electron donating groups and electron withdrawing group. Electron donating groups like methyl, ethyl, methoxy, they decrease the acidic strength by donating electrons to the benzene ring, making this negative charge destabilized. What about the electron withdrawing group like nitro, aldehyde, ketone, etc.? They withdraw electron and stabilize the negative charge. Hence, electron donating group decreases the acidic strength of phenol. Electron withdrawing group increases the acidic strength of phenols. Let's identify what these groups are. Methoxy is an electron donating group through plus R effect. Therefore, it decreases. What about the ketone? It is a minus R. Hence, it increases. Nitro is also minus R. It increases. What about the bromine? Although it exhibits plus R, it exhibits minus I as well. So, it is acting as electron donating as well as electron withdrawing. But which predominates here? Minus I. What about the methyl? It exhibits plus I and hyperconjugation. That means it's electron donating. What about the simple phenol? Here we have to compare it with hydrogen. Neither donates nor withdraws. So it will be in between the electron donating and electron withdrawing. So what all electron withdrawing groups we have? 2 and 3. So they have to be at the first. Where do we have it? You can see C, B and T. Then how do you determine which is more acidic between 2 and 3? Nitro is more electron withdrawing as compared to the ketone because here we have carbon and here we have nitrogen directly attached. Nitrogen is more electronegative. So that means it is exhibiting additional minus I effect also. And we have two oxygen to withdraw electron. Hence, nitro phenol will be more acidic than the keto phenol. Hence, 3 will be greater than 2. Where do we have 3 greater than 2? In option C. Therefore, the right option is C. However, let's verify here nitro first and then ketone. Since we have bromine also as minus I, fourth will be the next. And we have the phenol because there is no electron donating or withdrawing. And then comes the electron donating. What are the electron donating we have? Methoxy and methyl. Because methoxy exhibit resonance and resonance predominates over plus psi, this will be more electron donating. That means least acidic. So one should be at the end. Hence, the final answer is option C. So this is how you have to solve the questions. And if you still have any queries, you can comment your doubts in the comment section. And don't forget to subscribe the channel. Thank you.